Hydrogen. Hydrogen is the lightest and most abundant element in the universe, just one proton and one electron. It was first recognized by Henry Cavendish in 1766, who called it inflammable air, after noticing it formed water when burned. Later, Antoine Lavoisier named it hydrogène, or water former. Hydrogen powers stars through fusion, forming helium and releasing vast energy. On Earth, it's key in producing ammonia, refining metals, and powering fuel cells. Though a promising clean energy source, storage remains tricky. Compressed hydrogen typically costs $10 to $16 per kilogram. Helium. Helium was first detected in the Sun in 1868 via a yellow spectral line during a solar eclipse, later found on Earth by William Ramsay in 1895. It's the second lightest element and a noble gas, non-reactive under standard conditions. Helium cools superconducting magnets in MRI machines, enables deep-sea breathing mixtures, and fills balloons. Its lightness allows it to escape Earth's gravity over time. Most helium is extracted from natural gas deposits. Prices can range from $100 to $500 per 1,000 cubic feet, rising during global shortages. Lithium. Lithium, discovered in 1817 by Johann Arfvedson while studying petalite, is the lightest metal and floats on oil. It plays a vital role in energy storage. Lithium-ion batteries power everything from phones to electric vehicles. It's also used in ceramics, lubricants, and psychiatric medications for bipolar disorder. Though not essential biologically, lithium has medical and industrial value. Lithium carbonate prices surged above $80,000 per metric ton in 2022, reflecting booming demand from the EV and energy sectors. Beryllium. Discovered in 1798 by Nicolas Louis Vauquelin in Emeralds and Beryl, beryllium wasn't isolated until 1828. It's lightweight yet rigid, with high thermal stability and resistance to corrosion. Beryllium is used in aerospace alloys, X-ray windows, and nuclear reactors. The James Webb Space Telescope's mirrors use beryllium to maintain shape in deep space. However, beryllium dust is toxic. Prolonged exposure can cause a serious lung condition called berylliosis. It sells for about $600 to $800 per kilogram due to processing complexity. Boron. Boron is a metalloid, bridging the gap between metals and nonmetals. It was discovered in 1808 independently by both French and British chemists. Found in borax, boron is used in cleaning agents, fiberglass, fertilizers, semiconductors, and borosilicate glass, like Pyrex. It absorbs neutrons, making it vital for nuclear reactors. In biology, boron supports plant cell walls and nutrient flow. Elemental boron is priced at $5 to $20 per kilogram, though boron-based compounds and advanced materials can be much costlier. Carbon. Carbon is the foundation of all known life. Its unique bonding ability allows for the complexity of DNA, proteins, and fats. It exists in several forms: graphite, soft, diamond, hard, graphene, 2D sheets, and fullerenes, cage-like molecules. Carbon is essential in energy: coal, oil, natural gas, steel-making, inks, and carbon composites. While graphite is cheap, $1,000 to $2,000 per ton, high-end forms like synthetic diamonds or graphene can cost thousands per gram. Nitrogen. Making up 78% of the atmosphere, nitrogen was discovered in 1772 by Daniel Rutherford, who found part of air that didn't support life or flames. While inert as N2 gas, nitrogen is highly reactive in compounds like ammonia, which is key to fertilizers. It's also used in explosives, cryogenics, and food preservation. Biologically, nitrogen is essential in amino acids and nucleic acids, DNA, RNA. Liquid nitrogen is sold for 10 cents to 50 cents per liter. Nitrogen gas prices vary by purity and usage. Oxygen. Discovered by Joseph Priestley and Carl Wilhelm Scheele in the 1770s, oxygen was later named by Lavoisier. It makes up 21% of Earth's atmosphere and is vital for respiration and combustion. Oxygen supports life, fuels fires, and drives oxidation reactions. It also forms ozone, O3, shielding Earth from UV radiation. Used in steelmaking, rocket engines, hospitals, and wastewater treatment. Industrial oxygen costs 15 to 30 cents per cubic meter. Medical-grade oxygen is more expensive. Fluorine. Fluorine, discovered in 1886 by Henri Moissan, is the most reactive and electronegative element. Its isolation took decades due to the extreme danger it posed to chemists. A pale yellow gas, fluorine reacts with nearly every element. In compound form, it's crucial, used in toothpaste, fluoride, Teflon, refrigerants, and some pharmaceuticals. Fluorinated materials are also essential in uranium enrichment and high-performance plastics. Elemental fluorine isn't sold freely, but its compounds cost hundreds to thousands of dollars per ton depending on complexity. Neon. Neon was discovered in 1898 by William Ramsay and Morris Travers during studies of liquefied air. As a noble gas, it's completely inert under normal conditions. Though rare in Earth's atmosphere, neon emits a vivid red-orange glow when electrically excited, making it iconic in signage. It's also used in high-voltage indicators, lasers, and cryogenics. Its low abundance and high-tech demand make it expensive. Neon prices range from $1,500 to $3,000 per 1,000 cubic meters, with surges during chip manufacturing booms. Sodium. Sodium is a soft, silvery metal that reacts violently with water. Isolated by Humphrey Davy in 1807 through electrolysis of molten salt, its symbol Na comes from the Latin natrium. Sodium is essential in biology for nerve transmission and fluid balance. Industrially, it's used in streetlights, sodium vapor lamps, soap making, and nuclear reactors. In compound form, it's everywhere: salt, sodium chloride, baking soda, sodium bicarbonate, and lye, sodium hydroxide. Elemental sodium costs around $100 to $300 per kilogram, while table salt is traded globally at a fraction of a cent per gram. Magnesium. Magnesium was first isolated by Humphrey Davy in 1808. Light and strong, it's widely used in automotive and aerospace industries. It burns with a bright white flame, making it useful in flares and fireworks. Magnesium alloys are prized for their strength-to-weight ratio, appearing in bike frames, laptops, and aircraft. Biologically, it's vital, central to chlorophyll, and involved in over 300 enzymatic reactions in the human body. Bulk magnesium sells for $2 to $5 per kilogram, depending on purity and global supply. Aluminum. Though abundant in Earth's crust, aluminum was once more valuable than gold. The Hall-Héroult process, developed in 1886, made it cheap and widely available. Lightweight, corrosion-resistant, and recyclable, it's used in cans, planes, buildings, power lines, and smartphones. It forms a self-protecting oxide layer, preventing rust, unlike iron. Aluminum prices vary with demand and energy costs, but typically range from $2,000 to $2,500 per metric ton. Silicon. Discovered by Jöns Jakob Berzelius in 1824, silicon is the second most abundant element in Earth's crust, mainly in sand and quartz. As a semiconductor, purified silicon revolutionized technology. It's the backbone of transistors, solar panels, and microchips. Also used in ceramics, glass, concrete, and silicone polymers, used in medical and household products. Industrial-grade silicon costs around $2,000 to $3,000 per ton, while electronics-grade ultra-pure silicon can cost over $100 per kilogram. Phosphor. Phosphorus was first isolated in 1669 by Hennig Brand by boiling urine in search of gold, resulting in a glowing white substance. White phosphorus is dangerously reactive, while red and black forms are more stable. It's essential in biology, DNA, RNA, ATP, and agriculture. Phosphate fertilizers are critical for global food production. Overuse, however, can lead to water pollution and algal blooms. Phosphorus compounds like monoammonium phosphate sell for $500 to $900 per ton. Sulfur. Known since antiquity and once associated with hellfire, sulfur is a yellow solid and vital industrial feedstock. It's key in making sulfuric acid, the most produced chemical globally, used in batteries, fertilizers, and metal processing. Biologically, it's found in amino acids, like cysteine, and vitamins. It's also used in vulcanizing rubber and fungicides. Sulfur is widely available and affordable, selling for around $100 to $200 per ton. Chlorine. Discovered in 1774 by Carl Wilhelm Scheele, chlorine is a yellow-green gas with a sharp, suffocating odor. It's toxic in large amounts, but life-saving in small ones, used to disinfect drinking water, treat wastewater, and in household bleach. Industrially, it's key in PVC plastic, pharmaceuticals, and paper production. Chlorine gas sells for $300 to $600 per ton. Bleach and other compounds are common in consumer and industrial markets. Argon. Argon, discovered in 1894 by Lord Rayleigh and William Ramsay, is a noble gas, colorless, odorless, and chemically inert. It makes up about 1% of Earth's atmosphere and is used in welding, light bulbs, and semiconductor manufacturing to create non-reactive environments. Argon is heavier than air and safe, making it useful in wine preservation and document storage. Extracted by distilling liquid air, argon costs $30 to $60 per 1,000 cubic feet depending on grade and region. Potassium. Isolated by Humphrey Davy in 1807, potassium gets its symbol K from the Latin kalium. It's soft, silver, and violently reactive with water. Potassium is essential in biology, regulating nerve signals, muscle contractions, and heart rhythm. Agriculturally, potassium salts are used in fertilizers. It's also found in soap making and fireworks, producing lilac flames. Potassium chloride trades for $300 to $500 per ton and is critical for global agriculture. Calcium. Calcium, isolated in 1808 by Davy, is never found in pure form in nature, but is abundant in minerals like limestone, gypsum, and marble. Biologically, it's the most abundant mineral in the human body. crucial for bones, teeth, muscle function, and nerve transmission. Industrially, calcium is used in cement, plaster, water treatment, and steel refining. Bulk calcium compounds are inexpensive, selling for $50 to $150 per ton depending on type and purity. Scandium. Scandium was discovered in 1879 by Lars Fredrik Nilsson while analyzing rare earth minerals. It's a lightweight, silvery white metal that's classified as a rare earth element due to its geochemical behavior, though it's actually quite abundant in Earth's crust, just hard to extract. Scandium is used in aerospace components, high-performance aluminum alloys, solid oxide fuel cells, and even in sports equipment like baseball bats and bike frames. Its scarcity and separation cost keep prices high, around $4,000 to $20,000 per kilogram depending on purity. Titanium. Titanium was first identified in 1791 by William Gregor and later named by Martin Heinrich Klaproth after the Titans of Greek mythology. It's known for its strength, corrosion resistance, and lightness. Titanium is critical in aerospace, medical implants, and marine equipment. It's also found in sunscreen as titanium dioxide and in white paints and coatings. While titanium ore, ilmenite, is common, the refinement process is energy intensive. Titanium metal typically sells for $4,000 to $6,000 per ton, but high-grade alloys are more expensive. Vanadium. Discovered in 1801 by Andrés Manuel del Rio and rediscovered in 1830 by Niels Sefstrom, vanadium is a silvery metal often used in alloys to increase strength and corrosion resistance. Most vanadium goes into steel production. Vanadium steel is lighter and stronger. It's also used in vanadium redox flow batteries for large-scale energy storage. In small amounts, vanadium is essential in some enzymes in animals and bacteria. Vanadium pentoxide, used industrially, trades around $7 to $10 per pound. Metallic vanadium is higher depending on form and use. Chromium. Discovered in 1797 by Louis-Nicolas Vauquelin, chromium gets its name from the Greek chroma, meaning color, since its compounds are vividly colored. Chromium is prized for its hardness, corrosion resistance, and shiny finish, hence chromium plating, chrome, on cars and appliances. It's also essential in stainless steel production and is used in pigments, leather tanning, and wood preservation. Trivalent chromium is biologically necessary in trace amounts, while hexavalent chromium is toxic. Prices range from $10 to $20 per kilogram for bulk industrial chromium. Manganese. Manganese was officially discovered in 1774 by Carl Wilhelm Scheele and Johann Gahn. It's a hard, brittle metal that's essential in steel production, used to remove impurities and improve strength. Beyond steel, manganese is used in batteries, including newer lithium manganese types, fertilizers, and even ceramics. It's also vital in biology, found in enzymes that help detoxify free radicals. Manganese is widely available and relatively cheap, $1,500 to $2,000 per ton depending on form and demand. Iron. Iron has been known since ancient times and is the most used metal in the world. It's the core of construction, tools, vehicles, and machines. The Iron Age, around 1200 BCE, marked a major leap in human technology. Iron forms steel when combined with carbon and other elements. It's also biologically critical. Hemoglobin in red blood cells uses iron to transport oxygen. Despite its utility, iron rusts when exposed to oxygen and water unless treated. Iron ore is cheap, $100 to $150 per ton, while finished steel products vary based on grade and application. Cobalt. Cobalt's name comes from kobold, a mischievous spirit in German folklore, because miners often found toxic arsenic-laced ores instead of desired metals. Georg Brandt isolated cobalt in 1735. Cobalt is used in high-strength alloys, magnets, blue ceramics and glass, and rechargeable batteries, especially lithium cobalt oxide types in electronics. It's also essential in vitamin B12. Cobalt's price has spiked due to EV demand and mining concerns, ranging from $30,000 to $60,000 per ton. Nickel. Discovered in 1751 by Axel Fredrik Cronstedt, nickel is a silvery metal with excellent resistance to corrosion and oxidation. It's key in stainless steel, rechargeable batteries, coins, and catalysts. In batteries, it's found in nickel metal hydride, NiMH, and lithium, nickel, cobalt, aluminum batteries, NCA. Nickel allergies are relatively common due to its use in jewelry and metal coatings. Nickel is traded globally at around $16,000 to $22,000 per ton, depending on market fluctuations and purity. Copper. One of the first metals used by humans, copper's history stretches back over 10,000 years. Its Latin name, cuprum, comes from Cyprus, an early source of the metal. Copper is excellent at conducting electricity and heat, making it essential in electrical wiring, electronics, motors, plumbing, and architecture. It's also antimicrobial, making it useful in hospital surfaces. Copper's reddish color and durability make it a popular decorative metal. Prices hover around $8,000 to $10,000 per ton, depending on demand and global supply. Zinc. Zinc has been used since at least the 9th century in India, but it was formally identified in Europe in the 18th century. Andreas Marggraf isolated pure zinc in 1746. It's mainly used to galvanize steel, a protective coating to prevent rust, in brass, copper-zinc alloy, batteries, and skincare products like zinc oxide. Zinc is also vital in human health, supporting immune function and enzyme activity. Zinc is relatively abundant and affordable, trading around $2,500 to $3,500 per ton on the global market. Gallium. Gallium was predicted by Mendeleev and discovered by Paul-Émile Lecoq de Boisbaudran in 1875. It melts in your hand. Its melting point is just 29.8 degrees Celsius, 85.6 degrees Fahrenheit, and expands when it solidifies, making it unique among metals. Gallium is vital in electronics. It's used in gallium arsenide semiconductors, LEDs, solar panels, and high-speed circuits. It's also employed in medical imaging and thermometers as a non-toxic mercury alternative. Gallium isn't mined directly, but extracted from bauxite or zinc ores. High-purity gallium costs about $300 to $500 per kilogram, depending on tech-grade purity. Germanium. Germanium was discovered by Clemens Winkler in 1886 while analyzing a mineral called argyrodite. It fulfilled Mendeleev's prediction of an ecosilicon. This metalloid is transparent to infrared light and crucial in fiber optics, infrared optics, solar cells, and early transistors. Though it has been mostly replaced by silicon in mainstream electronics, germanium remains important in niche, high-performance applications. Germanium is rare and mostly recovered from zinc refining. Prices range from $1,000 to $2,000 per kilogram, depending on purity and use. Arsenic. Arsenic has been known since ancient times, infamous as both a poison and pigment, like Paris green. It's a metalloid that's toxic in many forms, yet still has industrial uses. It's used in semiconductors, gallium arsenide, wood preservatives, herbicides, and glass manufacturing. Arsenic compounds can also occur naturally in groundwater, especially in parts of Asia. Despite its toxicity, it's been studied in cancer treatments and electronics. Elemental arsenic isn't traded widely, but arsenic trioxide sells for around $2,000 to $3,000 per ton. Selenium. Discovered in 1817 by Jöns Jakob Berzelius, selenium was named after the moon, Selene, since it was chemically similar to tellurium, of the Earth. It's used in photocopiers, solar cells, rectifiers, and anti-dandruff shampoos. Selenium is also essential in small amounts for human health, part of antioxidant enzymes, but toxic in high doses. Some soils lack selenium, affecting livestock health. Selenium prices range from $30 to $70 per pound, with higher costs for ultra-pure semiconductor-grade material. Bromine. Bromine is a deep red-brown liquid at room temperature, one of only 2 elements in liquid form alongside mercury. Discovered in 1826 by Antoine Ballard, it has a strong, unpleasant smell. It's used in flame retardants, water treatment, pharmaceuticals, and photography chemicals. In the past, it was used in gasoline additives and pesticides, though many have been phased out due to toxicity concerns. Bromine is extracted mainly from brine pools. Prices generally hover between $3,000 to $5,000 per ton, depending on purity and application. Krypton. Krypton was discovered in 1898 by William Ramsay and Morris Travers while studying liquefied air. It's a noble gas, colorless, inert, and rare in Earth's atmosphere. Krypton is used in high-performance lighting, especially in flash photography, airport runway lights, and some lasers. It also has niche uses in insulating glass windows and gas discharge lamps. Because of its low abundance and energy-intensive extraction, Krypton is pricey. Expect prices of $500 to $2,000 per 1,000 cubic meters, depending on supply and grade. Rubidium. Rubidium was discovered by Robert Bunsen and Gustav Kirchhoff in 1861 using flame spectroscopy. It gives off a deep red hue, hence the name. It's a soft, highly reactive alkali metal, never found in pure form in nature. It's used in research, vacuum tubes, and specialized atomic clocks for precise timekeeping. It also shows up in biomedical imaging and studies involving the brain and heart. Rubidium compounds cost around $700 to $1,000 per kilogram. Pure metallic rubidium is more expensive due to its reactivity. Strontium. Strontium was discovered in 1790 in the Scottish village of Strontian. It's a soft, silvery metal that reacts quickly with air and water. Historically, it was used in red fireworks and old CRT television screens. Today, it's still used in pyrotechnics, metal alloys, ceramic magnets, and medical imaging. Strontium-89 treats bone cancer pain. Strontium is naturally occurring and usually safe, but the radioactive isotope SR90 is a nuclear fallout hazard. Strontium carbonate sells for about $1,500 to $2,000 per ton in bulk. Yttrium. Yttrium was first isolated in 1828 by Friedrich Wöhler, named after the Swedish village Ytterby, which is also the namesake of several other rare earth elements. It's used in LEDs, red phosphors, lasers, superconductors, and ceramic materials like YAG, yttrium aluminum garnet. Yttrium oxide is also key in making phosphors for CRT displays and microwave filters. In medicine, radioactive yttrium-90 is used in cancer treatment. Prices for yttrium oxide hover around $10 to $20 per kilogram, while metallic yttrium is costlier. Zirconium. Zirconium was discovered in 1789 by Martin Heinrich Klaproth and isolated in 1824. It's a strong, corrosion-resistant metal used in nuclear reactors because it doesn't absorb neutrons easily. It's also used in ceramics, abrasives, artificial gemstones like cubic zirconia, and heat-resistant parts. Zirconium alloys are found in spacecraft and chemical plants, where durability is critical. Zirconium metal prices are around $150 to $300 per kilogram, depending on form and industry grade. Niobium. Discovered in 1801 by Charles Hatchett, niobium was originally named columbium, after Columbia, a poetic name for America. The name niobium, after Niobe from Greek mythology, was later adopted internationally. Niobium is a soft, corrosion-resistant metal used mainly in steel alloys to enhance strength without adding weight. It's critical in pipelines, jet engines, superconducting magnets, like those in MRI machines, and even quantum computing. It's relatively rare. Prices range from $40,000 to $50,000 per ton, depending on purity and form. Molybdenum. Often confused with graphite in early studies, molybdenum was isolated in 1781 by Carl Wilhelm Scheele. Its name comes from the Greek word molybdos, meaning lead. Molybdenum has an incredibly high melting point and is essential in steel alloys for construction, aerospace, and military applications. It's also used in lubricants, catalysts, and nuclear reactors. Biologically, it's a trace element in enzymes that help break down toxins. Molybdenum prices typically range from $20,000 to $30,000 per ton for the metal, with molybdenite concentrate being cheaper. Technetium. Technetium was the first artificially produced element discovered in 1937 by Emilio Segre and Carlo Perrier. Its name means artificial in Greek. It's radioactive and doesn't occur naturally in significant quantities, though tiny traces exist in uranium ores. Technetium-99m is widely used in medical imaging, especially in bone scans and heart stress tests. Its short half-life makes it ideal for diagnostics. Due to its synthetic nature and use in healthcare, it isn't sold on the open market, but its production cost is significant and handled via specialized nuclear facilities. Ruthenium. Discovered in 1844 by Karl Ernst Klaus in Russia, ruthenium is named after Ruthenia, the Latin word for Russia. It's a rare platinum group metal used in electronics, wear-resistant coatings, and catalysts. It's also added in small amounts to titanium and platinum alloys to improve hardness. Ruthenium compounds show promise in cancer therapies and data storage technologies. As a rare metal, ruthenium prices range from $400 to $700 per troy ounce, or roughly $14,000 to $25,000 per kilogram. Rhodium. Discovered by William Hyde Wollaston in 1803, rhodium's name comes from the Greek rhodon, meaning rose, due to the rose-colored salts it forms. It's incredibly reflective, corrosion-resistant, and used in catalytic converters to reduce car emissions. It's also used in jewelry plating and electronics. Rhodium is one of the most expensive metals, with prices historically spiking above $500,000 per kilogram during shortages. Today, it trades around $10,000 to $15,000 per troy ounce, but is highly volatile. Palladium. Palladium was discovered in 1803 by William Wollaston shortly after rhodium. Named after the asteroid Pallas, it's part of the platinum group. It's used heavily in catalytic converters, hydrogen purification, electronics, dentistry, and jewelry. In fuel cells, palladium helps catalyze reactions between hydrogen and oxygen. Palladium has seen wild price swings, driven by automotive demand. Current prices hover around $1,000 to $2,000 per troy ounce, making it one of the pricier industrial metals. Silver. Silver has been used by humans for over 5,000 years, for coins, jewelry, utensils, and trade. Its Latin name, argentum, gives us its symbol, Ag. It's the best conductor of electricity and heat of any element, used in electronics, solar panels, photography, and antimicrobial coatings. Silver is also important in dentistry, mirrors, and catalysts. Prices fluctuate with the market, but generally range between $20 to $30 per troy ounce, or $700 to $1,000 per kilogram. Cadmium. Cadmium was discovered in 1817 by Friedrich Strohmeyer while analyzing zinc ores. It's a soft, bluish-white metal, toxic in significant exposure. Used mainly in rechargeable nickel-cadmium batteries, pigments, electroplating, and as stabilizers in plastics. Due to its toxicity, its use has declined in favor of safer alternatives. Cadmium is a byproduct of zinc production. Prices range from $2,000 to $3,000 per ton, though declining demand has kept it relatively affordable. Indium. Indium was discovered in 1863 by Ferdinand Reich and Hieronymus Richter, named after the indigo blue line in its emission spectrum. It's a soft metal used in touchscreens, LCDs, solars, and semiconductors. Indium tin oxide, ITO, is vital in modern display technology. Indium is rare and often obtained as a byproduct of zinc refining. Prices range from $200 to $400 per kilogram, with high-purity forms for electronics costing more. Tin. Tin has been used since the Bronze Age, alloyed with copper to create bronze. Its symbol SN comes from the Latin stannum. It's soft, malleable, and corrosion-resistant, commonly used in solder, plating, like tin cans, and alloys like pewter. Tin whiskers can be a problem in electronics, tiny filaments that grow and cause short circuits. Tin is widely available, and prices typically hover around $25,000 per ton, depending on purity and global supply. Antimony. Known since ancient times, antimony was used in cosmetics and medicines in ancient Egypt and China. Its symbol, Sb, comes from stibium, the Latin name for its sulfide mineral. Antimony is a metalloid with flame-retardant properties, often alloyed with lead in batteries, bullets, and solder. It's also used in semiconductors, ceramics, and infrared detectors. In small doses, it has medical applications, though it's toxic in larger quantities. Prices for antimony metal are around $10,000 to $12,000 per ton, depending on purity and demand. Tellurium. Discovered in 1782 by Franz Joseph Miller von Reichenstein, tellurium was named after tellus, the Latin word for earth. It's a brittle metalloid used in solar panels, cadmium telluride, thermoelectrics, steel alloys, and even rewritable optical discs. It improves machinability of copper and stainless steel. Tellurium is rare and usually obtained as a byproduct of copper refining. Market prices range between $40 to $100 per kilogram, but vary with tech demand, especially in solar energy. Iodine. Iodine was discovered in 1811 by Bernard Courtois when processing seaweed ash. It's a halogen and forms deep violet vapors when heated. Its name comes from the Greek ioides, meaning violet-colored. Essential for thyroid health, iodine is added to table salt to prevent deficiency. It's also used in antiseptics, contrast dyes for medical imaging, and disinfectants. In industry, it appears in polarizing films and LCDs. Iodine prices typically fall between $30 to $50 per kilogram, depending on purity and source. Xenon. Discovered in 1898 by William Ramsay and Morris Travers, xenon is a noble gas, colorless, odorless, and chemically inert under most conditions. It's used in high-intensity lamps, flash photography, ion propulsion for spacecraft, and anesthesia. Xenon is also used in medical imaging as a contrast agent in CT scans. Rare in Earth's atmosphere, xenon is extracted from liquefied air. It's expensive, about $1,000 to $5,000 per 1,000 cubic meters, depending on purity and supply. Cesium. Cesium was discovered in 1860 by Robert Bunsen and Gustav Kirchhoff via flame spectroscopy. Its name comes from the Latin cesius, meaning sky blue, referencing the color of its spectral lines. It's a soft, gold-colored alkali metal, so reactive it explodes in water. It's used in atomic clocks, the most accurate timekeepers, oil drilling fluids, and photoelectric cells. Cesium-137, a radioactive isotope, is used in cancer therapy and industry. Pure cesium costs about $70 to $100 per gram due to its rarity and reactivity. Barium. Barium was discovered by Sir Humphrey Davy in 1808. Its compounds were known earlier, often found in a heavy mineral called barytes. Barite. Barium sulfate is used in medical imaging for gastrointestinal scans. It's opaque to X-rays and not absorbed by the body. Industrially, barium is used in drilling fluids, fireworks, green color, and ceramics. Elemental barium is highly reactive and stored in oil. Barium carbonate trades around $300 to $600 per ton. Barium metal is more expensive and less commonly sold. Lanthanum. The first of the lanthanides, lanthanum, was discovered in 1839 by Carl Gustav Mosander. Its name means to lie hidden, referencing its earlier confusion with yttrium. It's used in camera lenses, optical glasses, nickel metal hydride batteries, and petroleum refining catalysts. It also improves the brightness and clarity of LCD screens. Lanthanum is relatively abundant among rare earth elements and is usually mined from monazite sands. Prices for lanthanum oxide are around $5 to $10 per kilogram. Refined metal costs more. Cerium. Named after the dwarf planet Ceres, cerium was discovered in 1803 by Jöns Jakob Berzelius and Wilhelm Hiesinger. It's the most abundant rare earth element and is used in catalytic converters, glass polishing powders, lighter flints, and as a catalyst in diesel fuel additives. Cerium oxide is also used in solar panels and fuel cells. Despite being a rare earth, it's fairly common and affordable. Cerium oxide costs about $2 to $5 per kilogram. Praseodymium. Discovered in 1885 by Karl Auer von Welsbach, praseodymium's name comes from Greek for green twin, due to its green salts and similarity to neodymium. It's used in aircraft engines, magnets, carbon arc lighting, and colorants for glasses and ceramics. It also contributes to high-strength alloys and fiber optics. As a rare earth metal, it's obtained through complex extraction processes. Prices for praseodymium oxide range from $50 to $100 per kilogram, higher for metallic or magnet-grade material. Neodymium. Also discovered by von Welsbach in 1885, neodymium means new twin. It's famous for its role in powerful neodymium magnets, used in headphones, electric motors, wind turbines, and hard drives. Neodymium is also used in lasers, UV protective glass, and colored ceramics. Its magnets are vital in green energy and miniaturized tech. Global demand is high, especially for EVs and renewable tech. Prices vary, with neodymium oxide costing around $70 to $150 per kilogram. The magnets themselves are significantly more valuable. Promethium. Promethium is one of the rarest elements on Earth. Discovered in 1945 by Jacob Marinsky, Lawrence Glendening, and Charles Coriel, it was named after Prometheus, the Greek titan who stole fire for humanity, a nod to its radioactive nature. It has no stable isotopes and occurs only in trace amounts in uranium ores, or is synthetically produced in nuclear reactors. Promethium is used in luminous paint, atomic batteries, especially for space probes, and scientific instruments. Due to its radioactivity and scarcity, it's not commercially traded. Prices are classified or project-specific when used. Samarium. Discovered in 1879 by Paul-Émile Lecoq de Boisbaudran, samarium was named after the mineral samarskite, making it the first element named after a person, Colonel Vasily Samarsky-Bikovets. It's primarily used in powerful samarium cobalt SM co-magnets, which perform well at high temperatures, ideal for aircraft, motors, and precision-guided weapons. Samarium is also used in nuclear reactors and as a neutron absorber. Prices for samarium oxide range between $30 to $60 per kilogram. Magnets are priced higher, depending on composition and grade. Europium. Named after the continent of Europe, europium was discovered in 1896 by Eugène Anatole Demarçay. It's soft, reactive, and one of the most efficient phosphors among rare earths. Europium is used in fluorescent lighting, LEDs, TV screens, and banknote security features due to its ability to emit red and blue light. It's also used in nuclear reactors as a neutron absorber. Europium oxide is costly, typically $300 to $800 per kilogram, due to both demand and complex extraction processes. Gadolinium. Discovered in 1880 by Jean-Charles Galissard de Marignac and named after Finnish chemist Johann Gadolin, gadolinium is a silvery white rare earth metal with interesting magnetic properties. It's used in MRI contrast agents, nuclear reactors, and high-temperature superconductors. Gadolinium compounds are also employed in phosphors for TVs and LEDs. Gadolinium is paramagnetic at room temperature and becomes ferromagnetic when cooled. Prices for gadolinium oxide generally fall between $30 to $100 per kilogram depending on purity. Terbium. Terbium, discovered in 1843 by Carl Mosander, is named after the Swedish village Ytterby, source of several rare earths. It's used in green phosphors for lighting and displays, in solid-state devices, and in terbium-doped fuel cells. It also plays a role in magneto-optical data storage systems. Terbium alloys help in creating strong magnets when mixed with dysprosium and iron. It's relatively rare and expensive. Terbium oxide prices typically range from $600 to $2,000 per kilogram depending on demand. Dysprosium. Dysprosium was discovered in 1886 by Paul-Émile Lecoq de Boisbaudran. Its name comes from the Greek dysprositos, meaning hard to get, due to the difficulty of separating it from other elements. It's essential in high-performance magnets used in electric vehicle motors and wind turbines, especially because it maintains magnet strength at high temperatures. Dysprosium is also used in nuclear reactors and control rods. Prices for dysprosium oxide typically range between $300 to $600 per kilogram. Magnet-grade material can cost significantly more. Holmium. Holmium, discovered in 1878 by Per Theodor Cleve, is named after Stockholm, Holmia in Latin. It has the highest magnetic strength of any element, making it valuable in solid-state lasers, nuclear control rods, and magnetic flux concentrators. Holmium-doped glass is used as a calibration standard in optical spectrophotometers. It's not used as widely as other rare earths, but is critical in certain niche technologies. Holmium oxide typically sells for $80 to $150 per kilogram, with refined metal priced higher. Erbium. Erbium was also discovered by Carl Mosander in the 1840s and named after Ytterby, Sweden. Erbium-doped fiber amplifiers, EDFAS, revolutionized fiber optic communication, boosting signal strength over long distances. It's also used in lasers, especially in dermatology and dentistry. Erbium tints glass and ceramics pink, and is used in nuclear technology as a neutron absorber. Erbium oxide prices are around $70 to $120 per kilogram, depending on global demand in telecommunications and medical sectors. Thulium. Discovered in 1879 by Père Théodore Cleve, thulium was named after the mythological ancient land of Thule. It's the second rarest lanthanide, but has growing uses in portable X-ray machines, lasers, and in some high-temperature superconductors. Thulium is also being studied for applications in cancer treatment and quantum electronics. Due to its scarcity and limited supply, thulium oxide prices range from $1,000 to $2,000 per kilogram. Ytterbium. Named, again, after the village of Ytterby, ytterbium was discovered by Jean-Charles Galissard de Marignac in 1878. It's used in stainless steel refinement as a doping agent in fiber lasers and in atomic clocks with record-setting precision. Ytterbium compounds also appear in cancer therapies and earthquake sensors. While not rare geologically, refining ytterbium is complex and costly. Prices for ytterbium oxide typically range from $100 to $300 per kilogram. Lutetium. Lutetium, the last of the lanthanides, was discovered independently by George Urbain, Karl Auer von Welsbach, and Charles James around 1907. Its name comes from Lutetia, the Latin anime for Paris. It's one of the densest and hardest rare earth elements used in PT scan detectors, catalysts for petroleum refining, and LED phosphors. Due to its rarity and specialized applications, lutetium is one of the most expensive rare earths. Prices for lutetium oxide typically range from $5,000 to $10,000 per kilogram. Hafnium. Hafnium was discovered in 1923 by Dirk Koster and George de Hevesy, predicted by Mendeleev and named after Hafnia, the Latin name for Copenhagen. It's corrosion-resistant, has a high melting point, and is excellent at absorbing neutrons, making it essential for nuclear reactor control rods. It's also used in aerospace alloys, semiconductors, and plasma cutting equipment. Because it's often found with zirconium and difficult to separate, hafnium metal trades at around $1,000 to $2,000 per kilogram depending on purity and form. Tantalum. Tantalum was discovered in 1802 by Anders Eckeberg and named after Tantalus from Greek mythology because of its unquenchable resistance to reaction with acid. It's extremely corrosion resistant and used in electronics, especially in capacitors for smartphones, laptops, and hearing aids. It's also used in surgical implants and jet engine components. Tantalum is considered a conflict mineral due to mining issues in Central Africa. Prices vary but typically range from $150 to $300 per kilogram for powder or wire form. Tungsten. Tungsten, from the Swedish tungsten meaning heavy stone, was discovered in 1783 by the El-Huyar brothers. Its symbol W comes from wolfram, another name for the element. It has the highest melting point of any metal, 3,422 degrees Celsius, and is extremely dense, used in cutting tools, armor-piercing rounds, filaments in light bulbs, and X-ray tubes. Tungsten is also essential in aerospace and military technologies. Prices for tungsten concentrate range around $30 to $50 per kilogram. High-purity tungsten metal can cost significantly more. Rhenium. Rhenium was discovered in 1925 by Walter and Ida Nodak and named after the Rhine River, Rhenus in Latin. It's extremely rare, one of the last naturally occurring elements discovered. It has a very high melting point and is used in superalloys for jet engines, as well as in catalysts for refining lead-free gasoline. Rhenium's scarcity and demand in aerospace make it one of the most expensive metals. Prices range from $1,000 to $2,000 per kilogram for metallic rhenium. Osmium. Osmium, discovered in 1803 by Smithson Tennant, is the densest naturally occurring element. Its name comes from the Greek osme, meaning smell, due to its pungent oxide. It is used in fountain pen tips, electrical contacts, and high-wear applications. Alloys with iridium are used in surgical implants and pacemakers. Osmium tetroxide is toxic but valuable in microscopy for staining biological samples. Osmium is rare and expensive, trading at $10,000 to $20,000 per kilogram depending on form. Iridium. Discovered alongside osmium by Smithson Tennant in 1803, iridium was named after Iris, the Greek goddess of the rainbow, due to its colorful salts. It's extremely corrosion-resistant and used in spark plugs, crucibles, cancer therapies, and deep-sea communication cables. Iridium alloys are used in pen tips and spacecraft components. It's also associated with the asteroid impact that wiped out the dinosaurs due to an iridium-rich geological layer. Iridium is one of the most expensive metals, priced around $4,000 to $5,000 per troy ounce. Platinum. Platinum, known to pre-Columbian South Americans, gained European attention in the 18th century. Its name means little silver, platina in Spanish. It's dense, malleable, and extremely corrosion-resistant, used in catalytic converters, jewelry, fuel cells, and electronics. Also vital in medical implants and cancer drugs, like cisplatin. Its scarcity and industrial demand make it a valuable commodity. Platinum trades between $900 to $1,200 per troy ounce, though prices fluctuate with economic trends. Gold. Gold has been known and valued since antiquity. Its chemical symbol Au comes from aurum, Latin for shining dawn. Famous for its beauty, stability, and rarity, gold is used in jewelry, currency, and increasingly in electronics due to its conductivity and corrosion resistance. It's also employed in dentistry, satellites, and even in cancer treatments. Gold is endlessly recyclable and doesn't tarnish, contributing to its enduring value. Gold typically trades between $1,800 to $2,500 per troy ounce, depending on the global economy. Mercury. Mercury, also known as quicksilver, was known to ancient civilizations. Its symbol, Hg, comes from hydrogyrum, meaning water silver in Greek. It's the only metal that is liquid at room temperature. Mercury is used in thermometers, barometers, fluorescent lights, and dental amalgams, though many uses have been phased out due to toxicity. It accumulates in ecosystems and is a serious environmental hazard. Elemental mercury is strictly regulated and trades for $30 to $50 per kilogram in controlled markets. Thallium. Thallium was discovered in 1861 by William Crookes via flame spectroscopy, named after the green spectral line it produced. Thallos equals green shoot in Greek. It's a soft, heavy metal, once used in rat poison and insecticides, now banned due to its extreme toxicity. Thallium also finds use in infrared optics, low-temperature thermometers, and semiconductor research. Despite its toxicity, small radioactive isotopes are used in cardiac imaging. Metallic thallium prices are roughly $1,500 to $3,000 per kilogram, depending on form and regulation. Lead. Lead has been known since ancient times. Its symbol, Pb, comes from the Latin plumbum. It's dense, soft, and easily shaped, once used in pipes, paints, and gasoline. Today, due to toxicity, its use is restricted. Still, it's widely used in batteries, shielding from radiation, and weights. Chronic lead exposure can affect the nervous system, especially in children. Refined lead is relatively cheap, around $2,000 to $2,500 per ton. Bismuth. Bismuth was often confused with lead and tin in early history. Today, it's known as the heaviest non-radioactive element, and ironically, one of the least toxic heavy metals. It's used in cosmetics, fire detectors, low-melting alloys, and as a lead replacement in bullets and plumbing. Bismuth subsalicylate is the active ingredient in Pepto-Bismol. It forms colorful, stair-stepped crystals when cooled slowly from a melt. Prices hover around $8 to $12 per kilogram, depending on purity and demand. Polonium. Discovered in 1898 by Marie and Pierre Curie, polonium was named after Poland, Polonia, Marie's homeland. It's highly radioactive. Just micrograms can be lethal. Polonium-210 is extremely dangerous and has been used in scientific instruments and, controversially, in targeted poisonings. It's primarily produced in nuclear reactors. Due to its intense radioactivity, it's not commercially sold. Its handling is restricted to specialized institutions. Astatine. Astatine is incredibly rare. Less than a gram exists naturally on Earth at any time. Discovered in 1940, its name derives from the Greek astatos, meaning unstable. All of its isotopes are radioactive, with extremely short half-lives. It's thought to behave chemically like iodine. Astatine shows promise in targeted cancer therapies, especially radiopharmaceuticals. It's not commercially available. Radon. Radon is a radioactive noble gas discovered in 1900 by Friedrich Dorn. It's produced from the natural decay of uranium in soil and rock. Odorless and colorless, radon can accumulate in homes, especially basements, and is a known carcinogen linked to lung cancer. It has been used in cancer treatment, though mostly replaced with safer alternatives. Not commercially traded due to its short half-life and health risks. Francium. Francium was discovered in 1939 by Marguerite Perret and named after France. It's the rarest naturally occurring element in the alkali metal group. Extremely unstable and radioactive, francium exists only in trace amounts and has no practical commercial applications. Most of what we know is theoretical, based on extrapolations from other alkali metals. No market price exists. It's produced synthetically in particle accelerators for research. Radium. Discovered by Marie and Pierre Curie in 1898, radium was once used in luminescent paints for watches and instruments. Its intense radioactivity made it seem magical, until health consequences were discovered. Today, radium is primarily used in limited cancer treatments and historical research. It glows faintly due to interaction with surrounding air particles. Radium is extremely radioactive and dangerous in unshielded form, not commercially traded. produced only in small quantities for medical or research purposes. Actinium. Actinium was discovered in 1899 by Friedrich Oskar Giesel. It marks the beginning of the actinide series. It glows in the dark due to intense radioactivity and has been used in radiation therapy and as a neutron source. Actinium-225 is currently being researched for targeted cancer treatment, particularly in radiopharmaceuticals. It's produced synthetically in reactors, no open market prices available, but it's extremely expensive and rare. Thorium. Discovered in 1828 by Jöns Jakob Berzelius and named after the Norse god Thor, thorium is a weakly radioactive metal found in nature. It's considered a potential future nuclear fuel. Thorium reactors produce less long-lived waste and can't be easily weaponized. Thorium is also used in high-end camera lenses and welding electrodes. Thorium oxide is available commercially, usually around $100 to $300 per kilogram depending on purity and source. Protactinium. Discovered in 1913 by Casimir Fajans and Oswald Goering, and later fully characterized by Otto Hahn and Lisa Meitner, protactinium's name reflects its role as a precursor to actinium. It's a dense, silvery metal that's highly radioactive and extremely rare. It appears in small amounts in uranium ores. Protactinium has few practical applications due to its scarcity and radioactivity, though it has been used in scientific research on nuclear structure. Prices are purely theoretical. 1 gram could cost several $1,000s, mostly for research purposes. Uranium. Known since 1789, uranium was named after the planet Uranus. It's the heaviest naturally occurring element and is radioactive, though very slowly. Uranium-235 is used in nuclear power and weapons due to its ability to sustain a fission chain reaction. Uranium-238 is more common and used in breeder reactors and armor-piercing ammunition. It's also used in glass coloring and scientific dating. Natural uranium trades at around $70 to $100 per kilogram, U3O8 form, but enriched uranium is far more expensive. Neptunium. Neptunium was the first transuranic element synthesized, discovered in 1940 by Edwin McMillan and Philip Abelson. It was named after Neptune, the planet beyond Uranus. It's a radioactive metal produced in trace amounts during nuclear reactions or as a byproduct in reactors. Neptunium has limited use in research and is studied as a potential fuel in nuclear reactors. It's not traded commercially and is handled only in specialized facilities. Estimated costs exceed $5,000 per gram. Plutonium. Discovered in 1940 by Glenn Seaborg's team, plutonium was named after Pluto. Plutonium-239 is fissile and used in nuclear weapons and some reactors. Plutonium-238 is used in radioisotope thermoelectric generators, RTGs, powering deep space missions like Voyager and the Mars rovers. Highly radioactive and toxic, plutonium requires strict handling protocols. No market price exists for public trade, but it costs thousands of dollars per gram depending on isotope and purpose. Americium. Discovered in 1944 at the University of California, Berkeley, americium is named after the Americas. It's used in commercial smoke detectors, americium-241, where it ionizes air and detects particles from smoke. Americium is also used in neutron sources and research on nuclear batteries. A gram of americium can cost over $1,500 to $3,000, depending on isotope and form, with prices managed under strict regulation. Curium. Named after Marie and Pierre Curie, curium was discovered in 1944 as part of the Manhattan Project. It's a highly radioactive metal used in space power systems, RTGs, and has a neutron source. Curium isotopes have potential in nuclear batteries and scientific research. Its intense radioactivity limits practical applications. Estimated cost is over $100,000 per gram due to the complexity of production and extreme handling requirements. Berkelium. Berkelium was discovered in 1949 by researchers at UC Berkeley and named after the city. It's a synthetic element with no large-scale applications, though it's used in scientific studies and to produce heavier elements like californium. Due to its rarity and radioactivity, berkelium is only produced in microgram amounts. Production costs are astronomical, potentially over $1 million per gram, making it one of the rarest and most expensive elements. Californium. Discovered in 1950, californium is another product of Berkeley's radiation lab. It's a strong neutron emitter used in neutron radiography, cancer therapy, and oil well logging. Californium-252 is the most widely used isotope for starting nuclear reactors and detecting explosives. It's one of the most valuable materials on Earth by weight. 1 gram of CF252 can cost $20 to $30 million, depending on purity and availability. Einsteinium. Einsteinium was discovered in 1952 in the fallout from the first hydrogen bomb test and named after Albert Einstein. It's highly radioactive and used only in basic scientific research. Einsteinium helped synthesize element 103, lawrencium. Due to intense radiation, it's difficult to handle and isolate. Microgram level quantities are produced, with estimated costs over $1 million per milligram. Fermium. Discovered in 1952, also from hydrogen bomb fallout, fermium is named after Enrico Fermi. Like einsteinium, fermium has no practical use beyond nuclear science and the synthesis of even heavier elements. It exists in vanishingly small quantities and decays quickly, making it extremely hard to study. Not commercially available, research-level quantities may cost hundreds of thousands per microgram, if even obtainable. Mendelevium. Discovered in 1955 by Albert Ghiorso and colleagues, mendelevium was named in honor of Dmitry Mendeleev, creator of the periodic table. It was produced by bombarding einsteinium with alpha particles. Mendelevium is a radioactive metal with no practical applications, used purely in atomic research. Due to its extreme instability and difficulty to produce, only nanograms have ever been made. No commercial price exists. Estimated costs exceed millions of dollars per microgram. Nobelium. Named after Alfred Nobel, nobelium was discovered in 1958 by a team of researchers in Sweden and the US. It is a soft, radioactive metal and part of the actinide series. It's produced in nuclear reactors or particle accelerators and is studied to understand the behavior of heavy nuclei. Its isotopes are short-lived and decay quickly. Nobelium has no commercial use and is not priced for sale. It exists only in laboratory-scale experiments. Lawrencium. Discovered in 1961 at Lawrence Berkeley National Laboratory, lawrencium honors physicist Ernest O. Lawrence. It's the last actinide and is extremely unstable and radioactive. Most isotopes have half-lives of only a few seconds. It's studied for theoretical nuclear chemistry and structure. Like others in this group, it's produced in microgram or picogram quantities, with no market price or real-world application. Rutherfordium. Named after physicist Ernest Rutherford, this element was first synthesized in the 1960s by both Russian and American scientists. It marks the beginning of the transactinides. Rutherfordium has no stable isotopes, with all known forms decaying within seconds. It has no commercial use and exists only in high-energy physics experiments. Production is extremely limited, with costs running into tens of millions per gram, if that amount could even be produced. Dubnium. Dubnium is named after the Russian town of Dubna, where it was synthesized in 1967. The naming was part of a historical naming dispute between the US and USSR. Highly unstable and synthetic, dubnium is known only through nuclear reactions and its decay patterns. It has no applications beyond nuclear physics. No price or quantity is available. Dubnium is produced atom by atom in particle accelerators. Seaborgium. Seaborgium was discovered in 1974 and named after Glenn T. Seaborg, a key figure in transuranic chemistry. He was still alive at the time, an unusual honor. All isotopes are radioactive with short half-lives. It exists purely for experimental physics to probe the limits of nuclear stability. Due to rapid decay and high production cost, it has no market price or practical application. Bohrium. Named for Danish physicist Niels Bohr, bohrium was discovered in 1981. It's another synthetic element produced in particle accelerators through heavy ion collisions. Bohrium has extremely short-lived isotopes, making it difficult to study. Its chemical properties are theorized to resemble rhenium. It only exists in research facilities. There is no price or application beyond basic scientific inquiry. Hassium. Named after the German state of Hesse, hassium was synthesized in 1984. It's one of the heaviest elements ever confirmed. Predicted to behave like osmium chemically, hassium is studied through indirect detection methods due to rapid decay. Half-lives are measured in seconds or less. Not commercially available, produced one atom at a time. Meitnerium. Named after Lise Meitner, who helped discover nuclear fission, but was overlooked for a Nobel Prize, meitnerium was discovered in 1982. It is incredibly unstable, with isotopes that exist for milliseconds. It has no real-world applications and is used only in experimental nuclear science. No pricing or production beyond a few atoms at a time. Darmstadtium, discovered in 1994 at the GSI Helmholtz Center in Darmstadt, Germany. Darmstadtium continues the line of transactinides. It's believed to share chemical characteristics with platinum, though only a few atoms have ever been made. Its half-life is under a second for most isotopes. Exists only for theoretical study. No commercial value. Roentgenium. Discovered in 1994 by German scientists, Roentgenium was named after Wilhelm Röntgen, discoverer of X-rays. It's an extremely unstable metal, possibly behaving like gold in chemical properties. Only a few atoms have ever been produced. With half-lives typically under a second, it has no practical use and is studied solely to understand superheavy element behavior. Production is limited to particle accelerators. No pricing exists. Copernicium. Named after Nicholas Copernicus, this element was synthesized in 1996 at GSI Darmstadt. Copernicium is expected to be a volatile metal. perhaps behaving like mercury, but its extreme instability makes it difficult to confirm chemical traits. Most isotopes decay within milliseconds. Its existence is confirmed via decay chains only, and it's purely of academic interest. Nihonium. First claimed by Japanese scientists at Riken in 2004 and officially named in 2016, nihonium is the first element discovered in Asia. Named after Nihon, Japan, it's highly unstable and only produced atom by atom via fusion reactions. Its chemical behavior is expected to resemble thallium, though this is still largely theoretical. Exists only for scientific prestige and nuclear chemistry research. Flerovium. Discovered in 1998 at the Joint Institute for Nuclear Research in Dubna, Russia, flerovium is named after physicist Georgy Flerov. It sits under lead in the periodic table, and early predictions suggested it might be a noble metal. Some isotopes have half-lives of a few seconds, longer than most superheavies. It's studied for hints at the theorized island of stability. No commercial application, with production limited to advanced nuclear labs. Moscovium. Moscovium was discovered in 2003 by a joint Russian-American team and named after Moscow Oblast. All isotopes decay rapidly, within milliseconds to seconds, so chemical properties are mostly modeled rather than observed. Moscovium is part of theoretical models exploring shell effects and nuclear structure near the island of stability. Its existence is confirmed via decay patterns only. Livermorium. Named after Lawrence Livermore National Laboratory in California, livermorium was co-discovered with JINR in 2000. Its chemical behavior is expected to resemble polonium, though this remains untested due to its short half-life. Livermorium contributes to studies of how nuclear forces behave in very heavy atoms. Exists only in a handful of atoms at a time. Tennessine. Tennessine was synthesized in 2010 by scientists from the US, Russia, and other collaborators, and named after the state of Tennessee. It is the second heaviest halogen and may share properties with astatine or iodine, but with substantial relativistic effects. As with others, it's synthesized one atom at a time and decays in under a second. It has no uses beyond fundamental nuclear research. Oganesson. Discovered in 2002 and named after Yuri Oganessian, a pioneer in superheavy element research, Oganesson is the heaviest known element. Although positioned with noble gases, it likely behaves very differently, possibly as a reactive metallic solid rather than a gas, due to intense relativistic effects. Its isotopes decay within milliseconds, and almost nothing is known about its chemistry. Oganesson closes the seventh period of the periodic table and symbolizes the current frontier of element discovery. Now that we've explored all 118 elements, let's take a moment to understand the bigger picture, the logic behind the periodic table. Because this isn't just a list of atoms, it's a system, a map, a cheat sheet to how matter works. At its core, the periodic table is organized by atomic number, the number of protons in the nucleus. As you move left to right, each element adds one proton and one electron. Simple enough. But it's the table's structure that reveals how elements behave. First, the rows. These are called periods. There are 7 of them. As you move across a period, electrons are added to the same energy level, and you move gradually from metals to nonmetals. Next, the columns, the groups. Elements in the same group have the same number of valence electrons, the outermost electrons that control bonding and chemical reactions. This is why elements in a group behave similarly. Some key groups. Group 1, alkali metals. Soft, shiny, and extremely reactive. Group 17, halogens. Reactive nonmetals, often found in salts. Group 18, noble gases. Inert, stable, full outer shells. Now let's talk blocks. The table is divided into 4 blocks, S, P, D, and F, based on which atomic orbitals the electrons occupy. S block, groups 1 and 2, plus helium. Simple reactive elements. P block, groups 13 to 18, a mix of metals, nonmetals, and metalloids. D block, transition metals, strong, conductive, often colorful. F block, lanthanides and actinides, rare earths and radioactive elements. This layout explains electron configurations and tells you how each element will bond. Next, periodic trends. These are predictable patterns you'll see across the table. Atomic radius. Decreases across a period, increases down a group. Ionization energy. Increases across, decreases down. It tells you how tightly an atom holds on to its electrons. Electronegativity. Also increases across and decreases down. This shows how badly an atom wants electrons when bonding. So, in simple terms, Elements in the top right, like fluorine, are small, greedy, and hard to strip electrons from. Elements in the bottom left, like cesium or francium, are large, loose, and easy to ionize. Why does this matter? Because these patterns help you understand why sodium explodes in water, but neon does nothing, why carbon forms 4 bonds, but helium forms none, why metals conduct, nonmetals insulate, and some elements decay. The periodic table isn't just for memorization, it's a guide to understanding atomic behavior, a tool for predicting chemical reactions, designing materials, and exploring the universe. So next time you look at the table, don't see it as a wall chart. See it for what it is, a blueprint of matter itself. Every row, every group, every trend, it's all connected. And once you learn to read it, you'll realize you're not just learning chemistry. You're learning how the universe builds itself, one element at a time,